question. For those of you taking testing, majority of you, CSCI 5100 and 6100. So if you are not attending a colloquium, your assignment will receive a score 0. So even if you submit, you get 0. Your assignment is conditioned on getting a non-zero score for your assignment. And also we do attendance in the beginning and at the end. So in case for some reason you cannot attend colloquium, you have to send an email or Daniel, and then we can allow you to attend via Zoom synchronously. So you have a question, right?
Oh, yeah.
Yeah.
I did it swipe out, and I didn't realize you have to swipe it in. When you take it once at the end, is it you have to swipe twice?
No. I meant one time.
Oh,
yes.
Okay.
Then you did it. Yes. You swipe either in the beginning of the colloquium or at the end, then you do the five. No, we have cameras here. Thank you.
All right, so I'm really excited today to introduce the speaker, Professor Danna Gurari. And Danna has been doing some really amazing work in the field of computer vision. And some of you are taking computer vision classes, right? They're gonna study her work, of course. And she's the founding director of the Image and Video Computing Group. And her research covers a wide range of topics from computer vision, machine learning, and human computer action, accessibility, and biomedical image analysis. And her team is really focused on creating systems that help us better understand and analyze the visual information around us and work really about making real world impacts. And along the way, Danna and her student won a lot of awards, like the Best Paper Award at CSW and SIG USC Innovation Award at SSNT and such, etc. And her research has been supported by important organizations like the National Science Foundation, Microsoft, Adobe, and Amazon, and so on. So today, the title of Danna's talk is Designing Computer Vision Solutions for Real-World Applications. Again, it's all about real-world impacts. And she's going to tell us three ways her team is addressing this misalignment issue between computer vision paradigm and the real-world application. The number one is about data sets. We're going to hear about creating large-scale data sets that will fill gaps in representing authentic cases. And second, algorithms. Designing efficient hybrid algorithm crowd partnership to compensate for algorithm shortcomings. And lastly, models. Introducing compact models that can perform tasks accurately with less computational expense. So, without further ado, please welcome Danna.
Hi, thank you for the kind introduction, Tom, and thank you for everyone for showing up. So, looks like this might not be working on me again. I'm gonna have to abandoning. I'm stuck at the computer. Okay. So, as Tom summarized, my goal. That's okay. Thank you. I'll figure it out. I'm going to talk about computer vision solutions that align with real world needs. And my inspiration has really come from authentic use cases over the past 15 years or so. And so I want to share about these use cases that all have a common user aim, which is to engage with visual data. So I want to introduce to you Eric, who is a blind person, Zoe, who is a basic science researcher, and Benjamin, who is a lay person. So Eric is a blind person who learns about the visual surroundings through a mobile phone app by taking an image, optionally asking a question about that image, having that sent off to a crowd or algorithms, and then getting back a caption or answers. Zoe is a biological researcher who is trying to come up with basic science discoveries about, in this case, cells and how, for example, they come together to build blood vessels. And Benjamin just likes, for fun, to edit images, such as taking a daytime image and making it look like it's in a, nighttime image and making it look like daytime, kind of a rainy atmosphere, okay? So the key problems that all these three users share is a lack of representation and efficiency from computer vision solutions. So what I'd like to do is spend the rest of the talk talking about how our team has worked on improved representation and efficiency. So as Tom summarized, I'll be talking about dataset challenges for more inclusive models, hybrid partnerships for collecting consistently accurate annotations with minimal human effort, and compact models for less computationally demanding results. So let's start off with the dataset challenges. In order to appreciate why I landed where I did and why it's so important, I think it's good to understand a little bit of the context of dataset challenges. And so if we look at what's happened over time, we had our first computer in 1945, first digital image about almost 70 years ago in 1957, and then we had the birth of the computer vision field officially in 1966. The research communities bubbled up between 1983 and 1990, and it's grown ever since. Come 2009, we had the first large-scale data set that was released. It's called ImageNet. Many of you may have heard about it. It's been in popular media a lot. This was the idea at that time that shifted was computer vision models were going to emulate a human visual system, learning from lots of experience. I was molded by this context because I came in and started my PhD in 2010. The idea is to accelerate progress by engaging a community. So you have some kind of test where you try to figure out if something is correct or not correct. And you put a bunch of computers at the task of doing that test, and you grade each one of those computers. So these are public data set challenges. That's what we do. We create tests, and then we evaluate those algorithms out there. So this is analogous to the test that us students would have experienced when we were in school. Similarly, optionally, these data set challenges will provide lesson plans, which are just training examples that can be used to learn how to do that test in itself. And the essential ingredients that go in each data set challenge are going to be test examples that have target results, a metric for assessing the similarity between each model prediction and the target result, and new challenges for the community to tackle, evidenced by data set analysis and model benchmarking. Because if the new tests aren't hard, what is the point of giving it to the community? So my team has created 17 data set challenges, 12 during my time in the CU probation period. So for context, I was an assistant professor for 4 years at UT Austin. And so much of my work has been informed by my time there. And we have had amazing sponsors who have enabled much of this work to become possible through funding. So the inception of this work actually came from Tamia in part, who helped build an application called VizWiz. And that was the seed that got planted. And between 2000 and 2015, many users came and leveraged this app and generated a lot of data. My team jumped in around 2017 and said, let's make some different data set challenges on VQA, classification, localization, captioning, saliency, semantics. We also explored additional ones as time grew on privacy, annotator differences, answer grounding, image quality assessment. And finally, the ideas we learned from the original work spawned off brand new data set challenges with different data. So I'd like to talk a little bit about this work that we have done. So my inspiration is that authentic use case. And this was similar to what I described with the user Eric, who was blind, who was trying to solicit guidance on understanding his visual surroundings. In that app, 11,045 people submitted 72,205 requests between 2011 and 2015. 62% of those requests were able to be used in this data set because the users of the application agreed for that data to be shared publicly. So we created this data set previous to my time here, but it's important context. We anonymize the data by transcribing the questions to remove people's voices, resaving images to remove metadata such as where they were located. We reviewed every single image many times to remove private information such as people's faces, information about their prescription pills, things in their mail, and much more. And then finally, we went and annotated the data through a combination of crowd workers and in-house annotators. Contributors to data annotation include 19 students. Their faces are shown here. and thousands of AMT crowd workers who provided over 5,000 person hours, equivalent to several years of 40-hour work weeks. There are three key themes of these data sets that I believe are novel. First is that these are the first image description data sets from authentic use cases, specifically the tree of different data set challenges noted there. So when I say these are the first image description data sets, this includes an image where you have a description of the image, such as a bunch of small light brown mushrooms in a green field, or you have answers to questions such as, is it edible or poisonous? Answer could be poisonous. We released 2 different data set challenges with visual questions and their answers and image captions. A unique challenge that emerged from this, and I'm gonna just highlight that there's a publication about each body of work here, and so I'm gonna fly through these, but if you ever wanna reference the publication, I kind of note in the bottom right corner, you'll see we'll go up through the years and when each one of these were introduced. So one unique challenge from this challenge was to determine if questions can be answered, because in the case of 29% of the visual questions, the question could not be answered, such as what is the expiration date? There is no expiration date within the image. Another unique challenge we observed was that we needed to be able to discard images showing private content because private content was observed in 10% of the submitted images. We also needed to be able to answer questions about private content because for about 1 of every 40 visual questions that were submitted, the person wanted to learn about private information. Leveraging this public app was better than never getting the answer about their privacy. Another unique challenge that emerged from our work was answering questions about text and describing images with text. We found that for 45% of the visual questions, there was a question about text, and text was present in 63% of images. And this was really novel at the time. Now it's perhaps taken for granted. Another unique challenge from this data set is that there's a need to account for a greater range of content size. Up until this data set came out, people weren't really taking zoomed in pictures to learn about something. And this population revealed that that's really important because typically a blind person wants to learn about an object. And so often the object sizes were very large. And the visual questions often were about, and then the visual questions that were about reading or counting were typically smaller regions than those trying to learn about objects. Notably, we found roughly half the visual questions ask about the salient object, which is the most prominent object in the scene, while many other visual questions ask about the features of the salient object. So again, this is a really an object-centric data set from authentic users. Another challenge that emerged from this data set that wasn't widely explored is handling image quality issues that emerge in the wild. People who are blind can't verify the quality of their images. For example, they might take an image where the content is simply unrecognizable, or it's really blurry, or it's too bright, or it's too dark, or what they're trying to take a picture of isn't properly framed, or they're obfuscating something with their finger, or the content they're trying to learn about is rotated. We found about half the images had quality issues, and we put out a challenge to be able to predict whether or not images could be recognized, the content in them, and also to assess what are the quality issues even when the content was recognizable, to give feedback. And inspired by the desire to bring the real needs of real users, we also emerged to a new data source. We crawled Stack Exchange, which is a public question answering framework where you can go on a website, I'm guessing many of you already explored it, and post a question amongst many different topics. In fact, there's 105 different topics, including like gardening, LaTeX. And so we went and we scraped that internet and grabbed visual questions with their answers. And in this case, what we found, just kind of comparing previous data sets to the new data sets, what you would see are simpler questions in the traditional data sets up until the release of this new data set. And what we found with the new data set is not only do you get a question, you also get context that people were providing to help clarify the question as directed through the Stack Exchange interface, but also the answers are much, much longer. So they were typically over 100 words long. And so this is a whole new framework, and it demands a whole new set of evaluation metrics. And so this is another use case, an authentic use case that we revealed that is even now revealing even new problems for us to explore that our future work is addressing. Okay, the second thing that happened from our data set creation era that we're still on is we provided the first data sets requiring models to analyze images from people with vision impairments where little or no training data was available. And why did we do this? While this is deemed to be a large-scale data set, and it's widely leveraged for benchmarking models, it's actually very, very small. We're talking about less than 50,000 examples, where, in contrast, what we're seeing over time is data sets are exploding, getting all the data on the internet. So you're getting millions and billions of examples happening for training. So we're talking about almost a trivial size at this point in time. And so that's one of the motivations for us to want to explore training models with limited or no training data. And then the other aspect is that at the time that the data set was released, and even I think now for many topics, there's a domain shift in what is present in the VisWis data set from what other people have been looking at. So for example, private information, you pretty much won't find in other data sets. It's very rare because often there's filtering rules when someone uploads their data to the internet that they can't upload something that is private. So there's a bias that happens with just the idea of uploading something. And that's how other people are making data sets, is using data from the internet. And then the other thing is just what people care about and are asking questions about is very different than what you would find from the existing data sets where it's cited people who are thinking, what should I ask? So for example, you have a picture of me. A lot of people were asking, is my shirt dirty? That might not be the first thing that comes to your mind. Okay, so there's a domain shift in the kinds of material that's coming up in these data sets. And the goal again is designing models that can learn from a few examples. So the model can be given typically 0 to 10 examples. Intuition is, if you've never heard of or seen a zebra, you probably could figure out what a zebra is if I told you it looks like a horse with black and white stripes. So it seems reasonable that our modern models should be able to do this. And so, inspired, we've released several data sets around this framework. We introduced the first instance segmentation data set to also have holes and large objects, because that's a bias from blind people. So basically, we chose categories that were compatible with other categories that had been localized in previous data sets. So things like microphones, watches, wallets, hats, and more. And then we also had novel categories that were very prominent in our data set. Apparently ramen is widely enjoyed by people who are blind. Okay, so we gave a new data set to the world with 8,000 instances that included 100 categories, that covered 100 categories and over 4,000 images. We also introduced a zero-shot classification data set, which was the first one from an authentic use case. As I mentioned, part of my inspiration for this body of work was ImageNet. ImageNet is still widely used for benchmarking across all spaces. And so what we did is we provided a framework that could be leveraging models trained for ImageNet on our data set by going through all of our images and labeling those that had the exact same categories in ImageNet. And we chose 200 ImageNet categories that we found were widely prevalent in our VisWis data set. And hopefully just from visual inspection, you can see a huge difference between the original images in ImageNet, which show examples of table links. This is an artificially crafted one where people took filters and that's made these lower quality. And then in the case of VisWis, the corruptions look very different. And also the kinds of link appearances look very different. So we launched that for the world to work on. And this is all about taking an existing model with no training examples and testing how well it can locate the categories in ImageNet in our VisWis dataset. Finally, inspired by all this work, we said we need a new data set. And the reason is because we agreed when we first obtained the data from the VisWis users that we would never release their private data. So in order to use the data, we obfuscated all, which means we didn't have any private data from blind photographers to encourage the development of privacy preserving knowledge. And so what we did, super fun project, is we made boxes with private information. So we went online and we bought fake prescription pills, we bought fake pregnancy tests, and we bought fake everything. Some of them were real, like real newspapers, but these were all props. And we put these in a box and we sent these to 26 individuals. And we asked them to go and take pictures of these objects in places where they would likely be using them. And so we also introduced the first privacy data set that leverages data from private people. And we are working with 728 images and 728 videos that we just finished segmenting. And we have one body of work, fingers crossed, hopefully it'll be accepted by the time this video goes live for YouTube. And we have other work that's under development to continue building new data set challenges off of this work. Okay, the last key theme in our data set challenges are going to be novel tasks. So these are tasks that have never been looked at before within the community. And the motivation was very simple. When you look at the data, sometimes you see that it makes sense for a model to return one answer, such as, is my monitor on? If you ask 10 people, they all say yes. However, sometimes they don't. Does this picture look scary? Sometimes people say yes, sometimes no. Or what is in this can? There's a whole slew of possible answers and so on, okay? And so the motivation is that there's ambiguity, and there's ambiguity for a lot of reasons. And so the idea was to design models that acknowledge ambiguity. So we started this work in 2017. This was actually award-winning work at CHI, just to say, is there ambiguity given an image and a question? We followed up with saying, well, how much? If you were to ask a crowd, can we predict how many different answers would be returned between 1 and 10 answers? Then we said, why? And there's many different reasons why there could be multiple different answers, such as it's unclear what content the question is asking about when the question is, what is the bus number? And you can see there's 805A on the bus and 2405 on the bus. Or because of things like the detail level, should we answer the question, what book is this? Because we're dealing with, maxi aids or also all the information below it. There's ambiguity in the question of which side of the room is the toilet on, synonyms, subjectivity, and more. Okay, so we made a task of predicting what ambiguity is there, if any, from the visual question. And then we had subsequent work, which thank you to Josh. He'll be presenting this work actually in a few weeks, which is trying to figure out the hierarchical details that are going on when describing something. Because it turns out from a number of our studies listed here that over and over, people are saying the level of detail we're getting isn't enough. We want to hear more about these objects. I know this is a book. I can feel it. I can turn the pages, right? Like we want more. And so what we most recently did is we introduced the very first challenge that supported subpart hierarchical semantic segmentation. So basically, describe what is the object, describe its parts, and then for each one of those parts, describe its subparts. So breaking down and decomposing these objects into their nested subparts through 2 levels. Okay, so that's going live. And that summarizes 17 dataset challenges inspired by authentic use cases. Of note, we track progress with public leaderboards for many of these challenges. Currently, we have 10 with public leaderboards. And so in those cases, we hide the ground truth testing annotations so that no one can see it. All they can do is submit predictions to our evaluation server, and our evaluation server returns a score. And this reduces the chances for models to overfit because we have rules about how many times people can submit their answers. We also invite all to join our AI challenges in an annual workshop. And so we have a website called bizwiz.org where we list all of the data sets that in some way leverage the VizWiz data. And we also have a workshop page where we describe our annual workshop that has now completed its 6th edition. Nearly 200 teams from academia and industry have participated in our official challenges over the past 6 years, meaning they have contributed to our annual workshop where we announce the winners. Our datasets publications have received over 1,000 citations. AI now exceeds human performance for captioning images, answering visual questions, and finding salient objects. And so the field is really moving, and it's very exciting for people who are blind, and for many others. So what is powering the innovation that we're seeing from the community? The key ingredients for state-of-the-art models, for people who are familiar with the space, and even probably many of you who aren't familiar with it, is the plug word of generative AI. So we're talking about neural network architectures called transformers that have a tremendously large amount of parameters and then are trained on massive amounts of data, typically with self-supervision. So basically, if you're trying to predict in the book a word of a sentence, you would hide the word and say predict it, and then you could evaluate to see if the prediction matched what was there originally. And the data is scraped from the internet. Okay. That's the premise. What's next? We are trying to account for the ambiguity regarding what image content a question asks about. This is part of effective reasoning towards an answer. So we have questions where there's no evidence in the image what the question reasons about, such as what is the expiration date when the answer is not available. We have the standard framework, which is what type of airplane is this? Well, people might all give different answers, but they're all looking at the exact same thing. But then we have instances where there could be multiple plausible answers because the subject of the question could refer to different locations. No one's ever looked at what is the subject of the question looking at. And so that's something we're working on currently. And we have under review a grant proposal on that idea. As far as what's next, we also are thinking about fast, grounded, holistic understanding of objects. So going beyond just the data set creation of developing hierarchical decompositions of objects to actually be able to ground all of them. So the model framework. And this is something we're working on with regressive language modeling for grounded captions and leveraging synthetically created data to do this. And then the last thing, which has actually gotten a seed funding grant, is supporting other visually impaired populations. To date, the community really only focuses on one type of visual impairment, which is ocular visual impairments. So these are people who have problems perhaps with their retina or something within their eye structure. But I learned from an incoming PhD student who is now in his second year, Jarek Reynolds, that there are other kinds of vision impairments that come from brain injuries. So mild traumatic brain injuries are actually a huge reason for vision impairments. One, there are many types of vision impairments that arise, but one that's really common is the fact that when you have a vision impairment, it means you have a processing unit that can only take in a smaller amount of data. When you have the same amount of incoming information and you have smaller amount of space for processing, fatigue happens because you don't have the same amount of work you can do with that information. And so what we've proposed and we're working on is actually creating something akin to noise canceling headphones, but instead vision canceling headphones, where we let the people who are wearing these devices or using these devices focus on a smaller amount of information so that they're not overwhelmed. So they have less processing, but they're also getting less stimuli is the idea. And then the last thing that's next that I'm talking about with various people is how do we go about making more modern and larger authentic data sets? The data I have described is over 10 years old by now. A lot of the interests of the modern world have moved on, and that's not reflected in VisWis. And so we do need a rebirth of a new data set that's bigger and more modern. And so this is not something that I believe will come from academia anymore. There are a lot of industry players who have a lot of power and money who are now collecting huge amounts of data, such as Microsoft Seeing AI, Apple, Google's Lookout, Be My Eyes, which is got Be My AI, and Envision, and more. And so likely any future data set would emerge from a partnership with industry at this point. And that's part of what's exciting as we've moved on to industry solutions now from an academic dream that I started on when I started with this work. So the summary here is new dataset challenges that are inspired by individuals with vision impairments. All right, deep breath. Moving on to next subject, hybrid partnerships. So we're going to move on to Zoe, the scientist, who is trying to figure out something in basic science, looking at huge amounts of data, and models just don't work for her because her data is unique. She's collecting different data that for the first time has ever been collected. And so this is kind of this is one example of many different things we've looked at over time. I started this work actually at the start of my PhD, and it's evolved over time. So we've looked at recruiting humans to correct models' mistakes. We've looked at engaging just enough humans to capture the entire crowd's intelligence. We've looked at relieving humans from annotating examples when they just wouldn't be helpful. And we've looked at involving humans interactively in real time with support from several sponsors. During the CU Boulder probation period, we have continued this line of work, and I don't envision it stopping. I think that this is really a huge, important direction for future work, is thinking about how we partner with algorithms and get consistently high quality annotations. We have two key themes that emerged during my CU Boulder probation period on tracking and on segmentation. So interactive segmentation, we proposed the very first work that said, given some kind of an image, you can take any kind of interaction you want with the image, and the model will know how to segment the content you wanted. And that was novel when we proposed it. To the disappointment of Josh, that excitement of printing out the first thing it's still exciting, but then Meta put out a model called SAM that all of a sudden blew it out of the water. And so that reinforces the importance of this body of work, but it also obsoletes kind of the need for what we had put out there at the time, I believe. We also have done quite a bit of work on tracking, and SAM 2 came out recently. So that also is going to be an interactive framework that similarly is doing what we're trying to do. The good news is for research, not for users, is there are holes in both of those frameworks, and we're working on those. And so I'm just going to talk about the tracking side, but we are working on both of those sides and the gaps that there are. And so one of the ideas is to solicit humans to re-annotate video frames where a model fails. So a video is a series of images, and so you want to figure out what is the minimum number of frames where you would bring in a human to annotate those frames. And the motivation is the gap of where existing models are today, and that's tracking dense collections of objects. And fortunately, we have a lot of people at CU Boulder who care about this, who we're able to partner with, and we're very grateful for them for giving us their data and talking to us about their real world challenges. So things like swarms of bees and schools of fish are things we're looking at here at CU Boulder. Okay, so the framework that we've been going from was introduced by Samreen Anjum, who has just recently graduated. And we have our frames over time. So our first frame, and then over time we have new frames. And so the idea is we get a reference template for the first frame. So you bring in a human to figure out what is the thing we're trying to track? What does it look like? And then we have a model that condenses that representation into a very compact embedding. Okay, so we're reducing the data size, the representation. And then we take that reference and we try to find it in the next frame. So we have an object representation, and we are looking for that object in every subsequent frame. And we produce a similar embedding for each one of those detections. And then we say, are those similar? If they're not similar enough, we are then going to ask a human to come in and annotate, because we suspect there might be an issue, because there should be high similarity over time between these object embeddings. Otherwise, continue to track. You're good. These are really similar embeddings. We don't believe there's a mistake. That's the idea. The key idea here is that we're trying to work with people's data where there are not large-scale labeled data sets, meaning we have novel representations of objects. Okay? And so given that, we don't have huge amounts of human annotated data. And so what we're working on is a self-supervised learning approach where we take unlabeled data and we learn how to figure out the representations, and key to that is figuring out the motion behaviors. So not just from a single frame, what's the representation, but actually over several frames, what are the motions we expect? And are we seeing similar behaviors? And so that's something we're working on. And currently our baseline method outperforms existing baselines when used with 2 different trackers on 3 data sets. So that's kind of our ongoing work that's built off of over a decade of work for myself. I'm very excited about this interactive framework. And I just saw Neelima, she's working on that body work up there, if you're curious about that afterwards. Okay, I want to conclude with the discussion of efficiency. As I mentioned in the first part of this talk on dataset challenges, the state-of-the-art models are doing amazing because they are grabbing so much data to train a huge amount of parameters. A huge amount of parameters is very computationally demanding. This is a huge mismatch from what happens for many real-world applications where a large amount of computation is not practical. So for example, we don't on device want to run our phones. We don't want to run these on our phones because our batteries will go very quickly and then we can't use our phones for other purposes. Same is true for our smart watches or smart glasses that are coming up. And these devices aren't going away. They're growing in society. Not only do we want these to be run on device for just the speed of faster purposes, but also you don't always have internet connection. And so if we think about the motivation for having more compact models, it's because we do want to avoid that large inference time. We want to avoid the large memory footprint. We want to avoid the large computational costs. And then, of course, we want to avoid that environmental cost that comes with running these models. So lots of good reasons for us to get away from that paradigm. And so the idea is compact models so they can be used for more applications more efficiently. So the scope of this work is going to be on a task called style transform, which is transforming the content of an image into a new style. There are many applications for this technique, things like entertainment, artwork, virtual reality, augmented reality, gaming, marketing, presentations, and training data generation. And I'm particularly excited about the last one. So the contribution in this body of work was the very first approach to use knowledge distillation to create compact models for photorealistic style transfer. And so photorealistic means if I show you the image, you won't know that AI was involved in manipulating it. So if we ask you, is this if this was AI influenced? If you answer no, we succeed. If you answer yes, we failed. So what we want is a student model that learns what the teacher knows with fewer parameters. And the way that it shows it knows what the teacher does is when it makes a prediction. Its predictions over some output options match exactly what it looks like from the teacher. And in this case, when we say knowledge distillation, when we are trying to distill the knowledge, we define the knowledge as the parameters that reside in that teacher. So the background of understanding and appreciating the work that we did in this space is how style transfer had worked up until we came around. It still works that way often, but we kind of made an improvement on it. So the solution was an autoencoder solution like this, very simple framework, where you have coming in the image, which is IC, which is the content image, and you have another image, which is the style that we want the content image to adopt. And what the encoder does is it extracts features, compact representations, describing the content and describing the style. And in the original work, the idea was that the content should be very well captured by an object recognition model, because the entire goal of an object recognition model is to say, I'm going to distill a representation that no matter what the background looks like or what the object looks like, what the scene looks like, I will know that that object is present. And so often higher level features are being used, meaning features that are deeper into a neural network. And for style, often people were using a combination of the earlier level features. There's many different ways that they were combining it, but basically those lower level features capture things like, the color, whether using vertical lines, horizontal lines, and so on. And then taking those features, no training needed, a transformation is applied to impose the style features into the content features. Okay, so now we have an infusion of the two kinds of features, which can be decoded into a stylized image. So that's what was going on. And beyond that, the state of the art, when we came around, became a parameter heavy architecture, because what was happening is that was working well at a course level. But if you looked at the style, if you zoomed into images, and you could do this with your naked eye. If you zoomed in, you'd find there was errors in the style and the fine-grained details. And so to counter this, a cascade of autoencoders were used. So basically, we were going to figure out first how to transfer over using our transformation. And we're going to create a new image where we transfer over just the course style, right? So you can imagine a painter up there and saying, here's the face, here's the body, right? Very coarse. We take that stylized image, pass it in, and now we're going to take the style at a finer grain level with the stylized image at the course level. And we're going to impose this new finer grained style set of features onto the image that we pass in. And we get a new stylized image that has a little bit more detail, right? We've done a second round of painting to add a little bit more detail to that image. And we do this over and over and over. And the state of the art became for autoencoders. That's kind of where the community settled on. And so our first key idea was let's create a single autoencoder. And so we introduced two pieces that made this work, a thing called blockwise training and novel skip connections, to create a model that achieved comparable stylized results with 30.3% fewer parameters while supporting higher resolutions than was ever supported before because we had a more compact model, and achieving faster stylization because there's less computation that needs to be done. And so I'm happy during the Q&A to go into details, but the key idea is what we have now is a parallel of the 4 different transformations that you can see here, right? Those are still happening. But now all the work that's happening by the decoder and the encoder is being trained into this one. All the work that's happening between this decoder and encoder is happening here. So we've condensed all of that activity into smaller, more computationally compact blocks. So that was the key idea of that work. And then we moved on to the distillation step, which was to distill a more compact autoencoder. So what happened in this framework, I'm just showing you a snippet of the architecture, but we matched the teacher structure. However, we use a smaller channel length per layer to preserve the teacher's information. And so here I only show 2 of the 4 encoders and the decoders, but there's 4. Just for this figure, it's helpful to look at them. And so the way that this worked is we distilled the most important teacher style features into the student encoder, okay? So in learning, we have a loss function that says, let's take the style representation, which is gonna be that up there. And we're going to do the difference between that, between those 2 values during learning. And we're gonna try to minimize that error. And how did we decide the channel length? We said, we'll take PCA on the original representation of the style feature, and we'll figure out how many channels are needed to preserve 85% of the amount. That's just a norm that's used in publications. That's what we chose. And so that's what we did for one of the loss functions. And then the other one was on the decoder side. Again, if you remember from the previous work, we're trying to get a decoder to do the work that previous work had leveraged an encoder and a decoder to do. And so what we did during training is we had the decoder learn what would come from the encoder at each one of those 4 stages, what we call in the cascade of 4 autoencoders. And so we have 3 different elements that contribute to the loss for the decoder, shown in orange. Again, happy to go into these in detail afterwards if anyone has questions, but that was the idea. And what we found is that compared to existing models, the distilled model variance ran 5 to 20 times faster, with at most 1% of the original parameters while yielding better results. So what's next? We are currently working on understanding the roles of the teacher layers, not for style transfer, but for other tasks, to inform what knowledge should we be distilling to the student. So in this third part, summary is we have more compact models to match real world needs. And so to summarize the talk, just to recap, I've talked about some contributions our team has made for better representation and efficiency. And we talked about dataset challenges for more inclusive models, hybrid partnerships for collecting consistently accurate annotations with minimal human involvement, and compact models for less computationally demanding results. There are many people to acknowledge what I presented. I did a few shout outs in this talk, but this has really been a huge effort from a lot of people, including from my time at UT Austin, that has informed a lot of where we've come here. And so I don't have time to acknowledge them all, but they're listed up here. I will acknowledge my current students, Chang Yen, who's still at UT Austin, Everly, Josh, Atarva, Jarek, Nick, Nilima, and Johan up there. And so this really is because of the work of my mentees, who are my inspiration for my work, including also my former mentees. I've had a huge amount of amazing collaborators. Also, thank you, Tom and Li Jun. And thousands of crowd workers, creators of the VisWiz application who made a lot of this work even possible. And then, of course, the funders who allow for us to do the work that we're doing. So with that, I'll open the floor for any questions.
So we have a lot of people here, also have more than 30 people online. So probably we'll start with the questions from the audience.
That's great.
On the slide also one we talk about network and decoder. It takes in the image and the style you want to transfer it to, but you said you don't gain it. So how is it that style embedding somehow valid on the image?
Okay, so the information, what happened when we started to train object recognition models, I'm going to go back to this slide. What we got for free when we trained models from the days of AlexNet, so 2012, is this behavior that occurred where the model would figure out how to break up the information that was captured into low-level information, mid-level information, and high-level information, where one layer is needed to capture what is the object, and the previous layers are used as the style to manipulate. We're changing like the style to figure out what is the object. So because we have this separation, that means when you pass these into a model and you pull out a representation, you can push in to the model the content image and say, I'm only going to grab this feature. And then I'm going to pass in the style image, and I'm only going to grab statistics about this feature, and I can put those together. And so that's the idea of how it works. And that's when I talk about the transformation, there are many different kinds of transformations. There's a lot of work in thinking about how do we merge that low level and high level information that network had separated. How do we merge that together? So that's like a whole area of research, but that's the intuition.
So the style, the input, the special style is not like a text embedding, it's this image itself.
It's an image embedding. That's right. Now, I will say, with the onset of generative models, we are in a space where you can use a text embedding and get out a stylized image. So that is possible, and it is happening. My team hasn't directly worked on it, but it's the future.
Another question from back.
Do you have data?
Can you speak up, please?
Yeah. Do you have data set for like the stylized and original content?
Sorry, can you say the question one more time?
Tailored examples for the content, original content, and the stylized.
Okay, so I think you're asking for the comparison between the content and the style, and I think you're getting a kind of a value in mind. Is that correct? Okay.
Even for training, you still have an objective to see where the stylized image matches the original style. Right?
Okay, so I will start off by saying this is a very, like many computer vision problems, evaluation is a very flawed approach, and this is true across the board, including many of the problems I showed up here, okay? Including classification from the days of ImageNet. With that caveat, the way it's done is a combination of traditionally quantitative and qualitative metrics. And so there's one of the more popular ones is called SSIM. Just a shout out, Alan Bovic, the creator of this, is moving to CU Boulder from UT Austin. He's coming us and joining us here. So if you want to talk to the person who created this and got very famous and got like Emmy Awards, I think, for it, then you can go. But that's one of them. And this is used also by, I believe, people on television. It's not perfect. And so traditionally, in order to publish in the space, you also need to do qualitative studies where you show a human different examples and you say which one do you prefer, or you show individually the images and you say, does this look real or not? There are different user studies that we have done with each of our publications that support evaluation. So that's how it's done. It's imperfect, but it's not clear how to do it perfectly.
I can ask a question.
Yes.
So over 6 years of workshop challenges, and then it's impressive to see more than 200 teams participated. So what is your observation in terms of the trend about the architecture approaches that's been changing and changing as you drive the research?
Yes. So as far as the trend, we've really paralleled what you've seen in every other challenge. Like, I think that what the innovations from the mainstream trickle down to all other areas. So we started out in the first years with CNNs and RNNs, and that's what everyone were using. Combination of an RNN, current neural network, and a CNN, convolutional neural network, to describe the image and the question, and then do some fancy work to decode question. And LSTMs were very common and cool. And then we've seen a shift over time to now where then it was, pre-training and using the right pre-training model. And now it's really zero-shot models because they're crazy amazing and they're trained on the entire internet of all the languages of, like year after year after year. So it hasn't shifted from what we're seeing in the mainstream. What I've been excited about is that we've helped the mainstream shift their direction to focus on things that matter to a certain population. So I think that we've had an influence on the mainstream more than seeing a difference in the kinds of models we are winning. Does that answer your question?
Yes.
Okay. Yes.
Yeah, kind of in that vein, if I'm building image classifiers, should I test on ImageNet, or do you think, generally speaking, it's very pointful for example?
My return question would be, what's your goal? Like, what are you trying to achieve in training your classifier?
Well, ImageNet was a competition.
Yes.
And
still is.
Still is, okay.
Yes, it still is.
Is it still relevant to get on the ImageNet leaderboard right now?
No. I mean, human performance was surpassed in 2015. So there are reasons to work on it, but it's not, yeah. So it gets to like, what's your reason? I mean, it's great in the sense that it's really easy it's a large scale data set. It's really easy to download and work with. And if you're learning, it's a really well understood framework. And so there's a lot of literature you can leverage to try to figure out what were all the innovations, and then how do I branch off and improve something elsewhere. There's, groupthink that you can leverage from and learning. And I don't think there's anything wrong in working to learn in that space. But if you want to do something innovative, in my experience and what I've tried to highlight in this talk, is generally you need to look at data other people aren't looking at to figure out where are things breaking. Yeah.
Inside the
Yep.
Perhaps a poorly phrased question from an ethics perspective, but I'm curious. You talked about cognitive issues permanently or temporarily affecting one's vision. If somebody were massively integrated into photos and we have large collections of those photos, would you expect there to be some similarities in that data set to the Viswins data set?
I don't know. Like, someone who is blind, they have good motor abilities, right? They probably have really great motor abilities because they've had to replace their sense of sight with their other senses through just life experience of figuring out how to work in the world. And someone who's drunk probably doesn't have, they can't walk a line, for example, right? And so I don't know, you might see similarities in some aspects, but it's not obvious to me that it would be I think you would probably find some unique things going on there as well. Yeah.
Suggesting
yeah, I wouldn't think so. Mm-hmm.
So I'd like to ask the question about your second research goal. So do you think in the future there will no no human involved in a X-ray annotation. Is this like the ultimate goal?
Is the question, will humans be involved in annotation going forward? Is that the question?
I mean, do you think in the future the model will be accurate enough to not have the human involvement?
Okay, will we get a place where we don't need to have hybrid partnerships, where humans come in and crack the mistakes to doing certain things? Yes, for many applications, yes. We are going there. It's been a pretty traumatic few years for researchers because the industry have come in and said, hey, everything that you were studying is now possible and in the hands of the world. And so I do think that trend's not going away. I think a lot of people's lives are going to be dramatically improved. We've already seen it with the blind community. And so we will find that a lot of use cases no longer need any human involvement. There will always be a space where humans need to be involved. And it may not always be a purely vision space. We're often moving into multimodal spaces. So I present this work as a computer vision work, but a lot of it is actually multimodal because I'm dealing with language and vision. And that trend will continue. So we're going to see partnerships emerge often more likely in that multimodal space. My hypothesis. Yes.
Question. So, how do you think, like, for example, I do Josh's voice kind of like, when the sense came up and you need to like turn the research direction. So do you have any suggestion or advice like this situation happened in our like PhD career?
Yes. One, if you are somewhere where the big players are looking, your chances of getting an internship or a job there are probably better because you're looking at something that they want to know about and they need to hire people who know something about that to continue their progress. That's the first part. The second part is, I think the first part is try to join. And if you feel like you don't want to join, then maybe you need to start looking at things they're not looking at. And so often I go to the data and I look at the data to see where do these things break down, because often the fine tuning that happens is not going to come from industry. In my, like they're trying to hit 90-95% of users' needs is my belief. And there's always going to be people who are left out and needs that are left out, which is where the hybrid partnerships come in. And so I would say, try to explore those tools with lots of diverse data to figure out where they break down, and that's your opportunity. You can also jump to new problems. I've worked on, hopefully you've seen from this talk, I've worked on a lot of different problems and they all kind of blend together, and what you learn from one problem really does translate to another, and that diversity that you get helps you see things other people can't see. So you can also shift if you're like really just hands up and just, I don't want to be a part of this mass movement.
So that question online, can we take one online question before we end?
Yes.
They're asking, could you go into the structure of your hierarchical classification model and what further applications do you see in that?
Okay, so we don't have a model yet. I mean, we benchmark models, but to be clear, we don't have a model yet. What we're working on is a future body of work. Wait, hybrid, can you say the question one more time? Hybrid or the hierarchical? Hierarchical, yes. So this is the model that we've started to toy with. And so, but we haven't designed it. Can you finish the question? It was applications of it, right? Oh, okay. So for sure, for people who are blind, I think this matters. But I think this matters also if you are trying to do manufacturing and you want to get inspiration of how are other people mixing and matching things. If you can do this kind of hierarchical decomposition, including with locating the hierarchical parts, now you can swap in, for example, Velcro for shoelaces easily. So you have this ability to start to become creative in new ways very quickly. You can also at scale analyze the data on the internet and see what's happening, what's not for, marketing, what are the trends in style. So it's pretty, I think it's pretty endless. I'm happy to go more if the person online wants it, but I think we are over, so I want to be mindful of that time.
All right, staying on speaker.